Hello, welcome back. Next, we will introduce how you can combine using the tables with first law. So first of all, let's recall what is first law. First law is conservation of energy, and we derived those following equations for a closed system. So the first one is Q minus W equal to delta E. Q is heat transfer, W is work, and delta E is the change of total energy of the system, which has three components: delta KE, the change of kinetic energy, delta PE, the change of potential energy, and delta U, the change of internal energy. That's the first option for first law if you have a closed system. Second option is very straightforward. You just divide every term in the first option by time. Q divided by time becomes Q dot, W over time becomes W dot, and dE over dt will be the right hand side. Q dot is called heat transfer rate, and W dot is called power. Okay, so that's a quick review about what first law is. And then next one, we're gonna explain how we do that by doing one example. Okay, so here is the example. What we have is a well-insulated rigid container. Okay, so be careful here. Well-insulated, what does that mean? You should realize there's no heat transfer because it's insulated. And then the next word, rigid container. This container is rigid. What does it tell you? It means constant volume. The volume of this container doesn't change. Okay, and the volume is given is 0.28 cubic meter. We also know the temperature. The temperature of the gas is at 100 Celsius. And we know initially what's inside the container is saturated water vapor. So that's point G. And then what's going to happen is we have a paddle wheel inside. And then this paddle wheel is rapidly stirring this water vapor. What is this paddle wheel essentially doing is to transfer energy from the rotation of the shaft into the water vapor. So this is one way to transfer energy, and it is done by work. Work is being added to the water vapor, or energy is being added to the water vapor through this paddle wheel. So if the water vapor receives additional energy, what is going to happen? The temperature and pressure will probably go up. In short, the energy inside the water vapor will go up. So you start from saturated water vapor, point G, and then you add more energy into it. Obviously, it's gonna become superheated water vapor. Okay, so when do we stop? We stop when the final pressure is 1.5 bar. Okay, the example asks for three things. The first one is to sketch the two diagrams, P versus nu and T versus nu diagrams. The second one is to find out the work, how much work is transferred from the paddle wheel to the saturated water vapor. And then the third one is look for the final temperature in Celsius. Okay, so let's do the first one. Let's sketch the two diagrams. Okay, so first of all, you have those two diagrams, P versus nu and T versus nu. Pressure versus specific volume, temperature versus specific volume. And then the first thing you always do is to draw the vapor dome. Draw the vapor dome. Steep, less steep. Steep, less steep. Okay. Steep, less steep. Okay, that looks better. Okay, so now we have drawn the vapor dome. So let's start from the first one, P versus nu diagram. Let's recall on the P versus nu diagram, you have constant temperature lines. Constant temperature lines. How do we sketch constant temperature line? It's going down first, you curve down first, and then straight line, and then you curve down again. Okay, each line represents a constant temperature because we have 2 points, initial temperature T1 and a final temperature T2. So for this problem, we're going to sketch two constant temperature lines, one for each temperature, initial temperature and a final temperature. So let's sketch another one, curve down, and then straight, and then curve down. Okay, so now the next question is which one should be T1 line? Which line should be T2 line? Do you remember the rule? The rule is the higher this constant temperature line is, the higher the temperature it represents. So T1 versus T2, which one has a higher temperature? T1 is the initial temperature, and then what's going to happen is energy is added into the water vapor through this paddle wheel. So if you add energy into this saturated water vapor, what's going to happen to the temperature? The temperature will go up. So T2 is higher than T1. If T2 is higher than T1, then the top line should represent the higher temperature, T2, and the lower line should represent the lower temperature, T1. Okay, next one, we need to locate point number 1. Where is point number 1? Point number 1 must be on T1 line because the temperature of point 1 is T1. And then where do we put point 1 on this T1 line? We know initially it's saturated water vapor, so it's point G. So where is point G on T1 line? Right on the dome. This is point G, and that's also my point number 1. Point 1 is just point G. Okay, and next 1, 2, 2. 1, 2, 2. What kind of process is 1, 2, 2? This is a rigid container, meaning volume doesn't change. Volume doesn't change. So what's going to happen to my x coordinate? X coordinate is specific volume, which is volume over mass. So now we know volume doesn't change, and then mass doesn't change, obviously, because it's closed system. So what's going to happen to the x coordinate nu? Nu will not change. If the x coordinate is constant, 1, 2, 2 must be on a vertical line. So 1, 2, 2 must be on a vertical line. So we can sketch a vertical line across number 1. Okay, so 1, 2, 2 must be along this vertical line because it is a constant volume process which gives you a constant x coordinate. Okay, so next one, we need to locate number 2. Where's number 2? Number 2 must be on this vertical dash line. And also number 2 must be on T2 line because the temperature of number 2 is P2. So number 2 must be at the intersection. This is number 2. So 1, 2, 2 goes straight up. This is the process 1, 2, 2 on a P versus nu diagram. Okay, so now let's do T versus nu diagram. On a T versus nu diagram, we have constant pressure lines. How do you sketch a constant pressure line? Curve up, and then straight line, and then curve up again. This is a constant pressure line. We're going to sketch two of them because we have initial pressure P1 and final pressure P2. So we need one for each. Okay, so the next question is, which line represents P1? Which line represents P2? Do you remember the rule? The rule is still the same. The higher this constant pressure line is, the higher the pressure it represents. So which one has higher pressure, P1 or P2? 1, 2, 2. The paddle wheel is turning, transferring energy into this water vapor. So water vapor will gain more energy. If water vapor gains more energy, what's going to happen to the pressure? The pressure will go up. So P2 must be higher. If P2 is higher, then the top line should represent P2 and the lower line should represent P1. Okay, so next one, let's locate point number 1. Where is point number 1? Point number 1 must be on P1 line, and also we know point 1 is saturated water vapor, which is G point. So point 1 must be on P1 line and G point. So this is where number 1 is. This is my number 1, and it's also G point. Okay, next one, 1, 2, 2. And 1, 2, 2, we know this is a constant volume process because of the word rigid. If it is constant volume, what's going to happen to my x coordinate, which is nu? Same as before, nu is equal to volume over mass. If volume doesn't change and mass doesn't change, specific volume, which is my x coordinate, cannot change. So for a process where you have constant x coordinate, it must be on a vertical line. So you can sketch a vertical line across point number 1. Okay, and then 1, 2, 2 must be on this vertical line. Okay, and then where is number 2? Let's locate point number 2. We know point number 2 must be on P2 line because the pressure of point 2 is P2. And also point 2 must be on this vertical dash line because it is a constant volume process. So we find number 2 at the intersection, which is here. So this is number 2. So from 1 to 2, it must be on this vertical line. 1, 2, 2, go straight up. Go straight up. And now you can easily tell what's the phase of number 2 because number 2 is located to the right side of the vapor dome, so it must be superheated. Okay, so now we've done the 2 diagrams and also we've proved the phase of point number 2 must be superheated water vapor. So that's question 1. Okay, and then we move on to question number 2. Look for the work during the process. How much work will be transferred from the paddle wheel to the water vapor? Okay, how do we look for work? We can start from first law. Let's start from first law. Okay, first law is Q minus W equal to delta E. And delta E has 3 components, delta KE, delta PE, and delta U. And before you use this equation, you should always check if your system is a closed system, because that's the requirement for this equation to work. Okay, so my system is within the dash line, and is it closed? Do you see any mass transfer? There's no mass transfer, so it is a closed system, so it's okay for me to use this equation. Okay, next one, what can we get rid of from this equation? We have this word well insulated, which means heat transfer is 0. So Q goes to 0. Well insulated, there's no heat transfer. Next one, what about delta KE? What is the change of kinetic energy for the gas? Initial velocity must be 0 at rest. Final velocity will also be 0 at rest. So there's no change in kinetic energy. Delta KE goes to 0. Next one, delta PE. What is the change of potential energy? Is there change in terms of height? Does the height of the water vapor change? No, it doesn't. So there's no change of potential energy. Delta PE goes to 0. So to find work, what you need is work is equal to negative delta U. Okay, and then we rewrite capital U into lowercase u, just like before. It becomes mass times delta lowercase u. Okay, and delta lowercase u. Delta means final minus initial, so it's lowercase u2 minus lowercase u1. Alright, so take a look. If we ever want to find work, what do we need to do? We just need to find 3 things. Mass of the gas, u2, and u1. We just need to find 3 unknowns in the right hand side, and then we can look for work. Okay, let's start from the first one. Let's start from mass. Let's start from mass. What is the mass of the water vapor? What is the mass of the water vapor? Is there any given condition that is more closely related to to mass? The one we have is probably volume, because we know the definition of specific volume is volume over mass. So is it possible for us to find mass from this equation? We do the algebra. Mass is equal to volume over specific volume. Okay. All right. So now we said specific volume must be constant, like before. specific volume must be constant because volume doesn't change and the mass doesn't change. So specific volume doesn't change. So it really doesn't matter which specific volume you use. You can use either nu1 or nu2, the initial specific volume or the final specific volume because it is constant. But here, let's choose nu1 because point 1 is point G. So then what you're essentially looking for is just point G, nu G, nu G. And how do you look for nu G? You can easily find nu G from the table. Okay, and do we have volume? Yes, volume is given. So the only thing I need to find is nu G at point number 1. Okay, so now, what do we know about point number 1, the initial point? Do we know pressure or temperature? We know temperature. We know the initial temperature is 100 Celsius. Like we did before, if you want to start from temperature, you go to table A2. If you want to start from pressure, you go to table A3. This time we know temperature, so we go to table A2. Okay, so we go to table A2 and we start from the temperature T1, which is given as 100 Celsius. And from the table, what do you want to look for? You want to look for nu G, and in our case, we call it nu G1 because it's at T1. Okay, so now let's go to the table. This time we need to go to table A2 because we start from temperature. Okay, so this is table A2. And now we look for temperature. The first column is temperature. We look for 100 Celsius. 100 Celsius. We go down. 100 Celsius is right here. And then the one we're looking for is nu G. So you go to the right. This is the row you want. And then what is nu G? Nu G is right here, 1.673. This is nu G. So we go back to our notes and write down this number. And don't forget the unit, cubic meter per kilogram. Okay, we found nu G and it's 1.673 cubic meter per kilogram. Okay, and then you plug in this number back into here. You can easily find mass. Plug in volume, 0.28 cubic meter SI unit, divided by nu G1, 1.673, also in SI unit. So the solution is 0.167, and the unit must be SI, which is kilogram. Okay, so this is how we find the first unknown in the right-hand side, mass, which is equal to 0.167 kilogram. And then we look for the second unknown, U1, and then the third unknown, U2. Okay, let's start from U1. Let's start from U1. U1. How do we look for U1? We know U1 point number 1 is just point G. So essentially you're just looking for UG. UG at number 1. UG. How do you look for UG? Very good. Same table. Table A2. You still start from temperature T1, 100 Celsius. And this time you look for UG. We call it UG1. Alright, let's go to the table. And we start from 100 Celsius, the highlighted row. And where's UG? UG is here. So the UG we want is 2500, 6.5. And do not forget the unit, kilojoule per kilogram. Okay, so now we go back to our table and we go back to our notes and copy down this number. UG1 is equal to 2500, 6.5 kilojoule per kilogram. So now we're done with U1. We're done with mass, we're done with U1. The only thing left is U2. Okay, how do we look for U2? Alright, like we said before you look for a property, in this case it's U, what you need to do is to decide what's the face of this point. So if you ever forget, let's go back to the diagram. What's the face of number 2? Number 2 is located to the right side of the vapor dome, so number 2 must be superheated. If it is superheated water vapor, you always go to table A4. Okay, always table A4. So now in order for us to find U2, we have to go to table A4. A4. Okay, how do we use table A4? You have to have two inputs when you use table A4. Let's take a look. Let's go to table A4. Okay, so this is table A4. You have to have two inputs. The first input has to be pressure so that you can find a corresponding block. Each block is at a different pressure. So for example, this one is at 0.06 bar. And then in addition to pressure, you need to have another input. It can be temperature, specific volume, internal energy, or enthalpy. Can be anything. Okay, do we have two inputs? Do we have two inputs? So do we know, we're looking for number two. We're looking for U2, final state. Do we know anything about the final state? Let's go back. Do we know anything about the final state? We know the final pressure is 1.5 bar. This is what we know. We know the final pressure, P2, is 1.5 bar. Okay, but like we said, we need two inputs whenever we use table A4. One of the inputs has to be pressure. Okay, so that's good. We have pressure P2, but we still need one more input. One more input. This one more input can be anything, such as temperature here, or nu, or u, or h. So can we find T2, or nu2, or u2, or h2? Which one do we actually know? Which one do we actually know? If you go back to the diagram, you will realize both those two lines on each line on those two diagrams is a vertical line, meaning they have the same x coordinate. It's a vertical line. They have the same x coordinate, which is nu. So nu1 must be equal to nu2. And do we have nu1? Do we have nu1? Yes, nu1 is right here. Nu1 is equal to nu g1. So we do have nu1. In other words, we do have nu2. Nu2 will be our second input. And the value of nu1 is 1.673 cubic meter per kilogram. And from here, you can find U2. Okay, let's take a look how we use this table. Okay, so let's go to table 4 first, and then the pressure we have is 1.5 bar. So look for the block corresponding to 1.5 bar. Here it is. This is the block we should be looking at. And then we're looking for U. Which column is U? 1, 2, 3. The third column is U. Okay, the third column is U. This column is U. The third column is U. Alright, and then what do we know? We said we know nu2. Nu is the second column, so we go to the second column. This is the second column. So we should start from the second column and look for the corresponding value in the third column. Okay, what is our nu2? What is our nu2 in the second column? We should look for our nu2, which is 1.673. Can you find 1.673 in the second column? Not directly, but our new 1.673 is between those two numbers. So what should be the corresponding U2? It must be between those two numbers, circled in red. Alright, so obviously we have to use what? Interpolation again. Okay, interpolation again. Okay, you can do interpolation yourself because we've practiced several times. You can do it either by hand or, for example, with the help of Excel. Okay, so U2 through interpolation is 27 67.8. And don't forget a unit, kilojoule per kilogram. You need to find it through interpolation. Okay, so now finally we have everything in the right hand side. U1, U2, and mass. Okay, so now we can easily find work. Work is equal to negative m U2 minus U1. Okay, plug in the numbers. Mass is 0.167 kilogram, so that's SI unit, minus, multiplied by U2. U2 is 2767.8 kilojoule per kilogram, minus U1, 2506.5 kilojoule per kilogram. Okay, those two have the same unit, kilojoule per kilogram, multiplied by kilogram. Okay, so our solution is negative 43.6. What is the unit to my solution? The 2 kilograms will cancel each other, so the unit that is left is kilojoule. Alright, so that is the solution to work, is negative 43.6 kilojoules. Does it make sense to have a negative number as the solution to work? Remember what the negative work means. A negative work means your system consumes work, while a positive work means the system generates work. Okay, my system is the water vapor. My system is the water vapor. And the pedal wheel does work to the water vapor. So that means water vapor consumes the work. Consuming work, that means you must have a negative number for work. So my solution as a negative number to work is correct. Okay, so that's question number 2. Look for work. And then the third question is to look for final temperature. So we're looking for T2. Third question is to look for T2. Temperature is also a property. Like we said, if you're looking for the property of a substance, the first thing you need to do is to decide what's the phase of this point. What's the phase of number 2? If you ever forget, you can always go back to the diagrams. Point number 2 is to the right side of the vapor dome, so point 2 must be superheated. If you're looking for the property of superheated water vapor, you should always go to table A4. Table A4. Okay? And remember, how do you use table A4? You have to have 2 inputs, and we do have 2 inputs. We just repeat. The first input we have is pressure. The final pressure P2 is 1.5 bar. We also know nu2, just like before here. Nu2 is equal to nu1, and it's 1.673 cubic meter per kilogram. And from here, you should be able to look for T2. Okay, let's take a look. How do we look for T2? How do we look for T2 from the table? So which column? We go back to here, this block, highlighted block, and then we're looking for temperature. Which column is temperature? First column is temperature. First column is temperature. So this time we highlight the first column. And then we know nu. We know the nu we have. Our nu is 1.673, and it's somewhere between those two highlighted numbers, 1.570 and 1.695. So what should be our temperature? It must be between the two corresponding temperatures, 240 and 280. And again, we just perform interpolation, and then you can find a corresponding temperature. Okay, go back to our notes. This time you perform interpolation again, and then find T2. The corresponding T2 is 273. And don't forget the unit. And what is the unit for temperature in this table? It's not Kelvin. Pay attention. If you forget, just go back to the top of the table, and you can see the unit is Celsius. Okay, so now go back to our notes and write down the unit is Celsius. 273 Celsius. And is that a unit that the question asks for? Let's go back. Yes, it looks for temperature in Celsius. Okay, so that's good because we give our solution is in Celsius. Okay, so that's this example.